Good morning, everyone. Welcome to this video lecture series on module number 3, that is time response analysis, okay, of control system engineering. So, in the previous video lectures, what we have seen is we have gone through a detailed study of block diagram representation, and then we have seen the signal flow graph concept, and we have drawn the various methodology to draw the signal flow graph, to understand the signal flow graph. Okay, so similarly now we'll go with the module number 3 today. Okay, now before going to module 3, let me make it more clear. In module number 3 we will be seeing first the time response analysis. You know what do you mean by response? Okay, response is something where whatever you give the input to the system, it has to respond. Okay, no doubt all the system, all the devices, all the networks, all the circuit will respond for the given input. Okay, now after responding to the given input, you need to analyze. Okay, that is the main concept here. Okay, and for the given response or for the obtained response, okay, when you analyze, then the analysis should be in time domain. Okay, so that is the topic here, is the time response analysis. Okay, for the given input, you need to, the system will respond, and for that responded system you need to analyze the signal. Okay, and the signal should be in time domain, or simply you can call it as a continuous signal, or a signal with respect to time t. Okay, and all the module number 1 concept, module number 2 concepts will be linked to the module number 3. Okay, we have seen in the module number 1 about the control system, how the control system is operated, what do you mean by control system. Then we have converted into the block diagram for further simplification to obtain the overall transfer function or the system function, right? And then we have obtained the overall transfer function till module number 2. But now in module number 3, for the obtained transfer function, that is nothing but the response of the transfer function, whatever you get after applying the block diagram reduction rules or by simply solving the signal flow graph, you need to analyze now. Okay, you should go in detail. Now we will go in much in detail about these applications. So now the time response, what we see here is, we go with some introduction. Time response, then what are the input applied to the system, then we try to study the steady state response and what is error, and time response specification, and few limitations related to this system response. Okay, so what is this time response? Here is introduction part. Okay, so in introduction part, you can see here the time response is defined as the output of the system when subjected to an input which is a function of time. Okay, so the definition says that if you have some system, okay, for example, you take any system, okay, and for that particular system, and if you are applying some kind of input to that system, and which is a function of time, then that particular system is nothing but time response of the system. Okay, for example, if you are applying some input to your laptop, okay, and your laptop is responding to you with respect to time, that is it can be a real time also. Okay, so that system is nothing but response of the system, how well my system will respond for the given input applied. Okay, and it will produce the output. I will give you one more example with related to this time response. Is, for example, if you have a printer, okay, and if you want to print a given some information on the paper, okay, so as soon as you give input to the computer, that is print option, okay, the printer has to print, that is the output. Okay, so how fast your system is responding for your given input, right? If you are giving, or if you are pressing the print button here, and if you are not getting the printed paper immediately, then that system will not be according to the time, because it is not following the time. There is a kind of a bit delay there. Okay, so therefore how we define the time response of a system here is, if you are getting the output with respect to the input, which is function of time. Okay. Similarly, the time response analysis means the subjected the control system to input that are function of time, okay, and studying their output which are also function of time. Okay. For example, if you are giving some input to the control system, now we will speak only in terms of control system. Okay. Now if I take an example of the fan, okay, so I will give an input to the fan by turning on the button or turning on the switch. Okay. So the turning on of the switch is nothing but my input to the system, because it's a control system. I will just turn on the system. Okay. So what is the output of the system now? The output of the system is your fan is rotating in, right? Your fan is rotating in the sense what? It is in function now. Now, once the fan is rotating, you need to study the output. Okay, that is called as studying of the output, which is also a function of time, right? Fan is rotating with respect to time t, right? According to time seconds 1, 2, 3, 4, 5, 6, 7 and all, your fan is still rotating, right? So I have applied the input. Okay, now fan is in function. Now after this, you need to study the output. Study the output in the sense how well my fan is rotating, at what speed my fan is rotating, right? Whether the speed is acceptable, or whether I want to increase my speed of the fan by 1, 2, 3, 4 and 5, whether I need to minimize the fan speed, whether I want to maximize the fan speed. Okay, so this is nothing but your response of the system, and we will analyze this. So what we have done, we have applied the input, we got the response from the fan that it is rotating with respect to time t, and then analysis, that is nothing but the last part. The last part is nothing but you need to analyze. So what we have analyzed, based on the rotation knob of the fan control, we analyze the speed of fan, and based on the analysis of the speed of the fan, we try to control this functioning of the fan. That is nothing but, again, it is also with respect to time t. So therefore, how we define the system function here, or how we define the time response of the system? Any system, when we apply some input, and that system will produce some output with respect to time. Such systems are known as time response of the system. And when you analyze those system output, then that becomes time response analysis. Okay. Then once you understand this, you need to understand the time response. Okay. So how to understand the time response is, a given control system generates an output or response for a given input. Yes, we know this. For any control system, when you apply some input, then that particular control system will generate the output. Okay, this is the first point. The second point says that the input represents the desired response, while the output is the actual response of the system. Okay. For example, if you want to give some input to the control system, that becomes your desired. Okay, it is my desire that, for example, if you are operating a small a calculator, okay, and you are doing some calculation like 2 plus 4 is equal to 6. Okay, so what is your desired value now? You want 6 after calculation. So what input you are giving? 2 plus 4 is your input. Okay, and what is the desired output? It should be 6. Okay, so therefore when the calculator will do the operation, it will produce the output at 6. That 6 is nothing but your actual response. Okay, so in this way we try to understand the concept of time response with respect to the control system. So example here, what they have taken is, that is elevator. Okay, you know what do you mean by elevator? Your desire is you want to go to the first floor, right? So you take an elevator, okay, and then you just press the button. Which button? Elevator. In elevator you have seen, right? Or in the lift you have seen. Once you enter into the lift, you want to go to first floor, second floor, third and fourth floor. There are buttons available in the lift, right? So you press 1, 2, 3, 4, 5 or sometimes ground button, right? For example, you have pushed the 2, means if you want to go to second floor, right? So that becomes my desired value. Okay, now once the lift operates, and if it takes you to second floor, then that becomes your actual response. Okay, but instead of taking it to the second floor, if your elevator or the lift take you to the third floor, then that does not becomes my actual response, or that do not becomes my desired response. My desired was I want to go to second floor, but my desired is taking me to third floor. So that is the reason I cannot go for such type of control system, such type of time response. So therefore, this is how we go for representing our time response. Then how you try to define the time response with respect to graphical representation. Okay, so what we have defined here in earlier part is time response is the response of the control system as a function of time. You have seen in the signals and system that all the signals are varying with respect to time t. Same thing here. Okay, so but this time response here, they are divided into two parts. The first part is called as a transient response, and the second part is called as a steady state response. Okay, so what do you mean by the transient responses? The output is changing with respect to time t. Okay, so how you define the transient responses? If you are applying some input to this control system, and that particular system is getting me some output with respect to time t, that is, change in the output is because of change in the input. So that response is called as transient response. We can see here in the graph that in the graph, this first block is my transient response. Okay, now what do you mean by the steady state responses? The output is almost constant. There is no change in the output. No change in the output in the sense, you take an example of a fan, okay, and you have, for that particular fan, you have a regulator to control the speed of the fan. Okay, so what we will do is I will just give you the input button 1. Okay, now if I go on changing my regulator, but my fan is not changing the speed, it is constant at one level itself, then those type of systems will fall under steady state response. Okay, where the output will not change, the output will remain constant for a time t. This is also with respect to time t only. Okay, there is a no change in time t irrespective of change in the input or change with respect to time t. Such type of response are nothing but your steady state response. Okay, so how this can be understood, how this can be applied is we will see here. Okay, with respect to time t. Now see here in time response, okay, we will go for calculation of the total time response. Okay, total time in the sense from your start of machine to the end of machine, which also include the operation of machine, okay, or operation of the system. So how we define here the total time is, the total time is represented by c of t. Okay, and c of t followed by the steady state response css of t. Here ct, it represents, it's the total time response. Ct means total time, or simply you can call it by transient time. Sorry, we will take in terms of in other way. Here ct represents my transient time. Okay, and this css represents my steady state time. Okay, and what is the total time? Total time is nothing but it is the algebraic sum of transient time plus steady state response of the time, or steady state response. Okay, so therefore we, if you look at this particular graph, in this graph, okay, this line is along the time, this is along the response. So when I apply input to my system, my response, if it is going high till this maximum point called a point, and this we call it as a maximum overshoot. Maximum overshoot is nothing but it's the peak of the point where your output of the system is maximum. Okay, so it is called as maximum overshoot, and then once it reaches to this particular point, it will remain constant. It will remain constant, just like your low pass filter and high pass filter. In low pass filter, it transmits all the frequencies and it will avoid the high frequencies. And in terms of high pass filter, it allows all the high frequencies and it will reject all the low frequencies, right? So you can see there is a graph, there is a constant in the frequency response. Okay, so those systems are always varying with respect to time t, where if we measure the response of those system, that is high pass filter and the low pass filter, let it be first order filter or the second order system. Okay, you can see there is some bit of variation. There is no any constant term. We find only the constant term after some particular frequency called as a cutoff frequency. Same thing here also. Once the applied input reaches to this maximum frequency f max, then the output will remain constant. It remains constant, or simply it will go on decreasing. Okay, you can see the signal get decreasing, but at some particular point it vanishes. Okay, so if you measure this type of response, then you will able to find the total response of the system given by Ct of t plus Css of t. This Ct represents my transient response and Css represents my steady state response. Okay, then what input should be applied to the system? Okay, for time system response analysis of the control system, we need the system to be various test inputs in the sense, you have seen in the signal system, you are going for analysis of the signals, right? You have taken many signal systems. Okay, and how my system will respond for those particular systems, we will see. Okay, now have a kind of imagination that you have one system and you are applying some input and it will produce some output. Okay, we don't know what we are applying now and we don't know what we are getting now. Okay, now what does this system applied systems are? We will test some kind of standard signals. You have studied in the signals and system some standard signals like inputs, impulse signal, unit step signal, ramp signal, parabola, and sinusoidal signals. Okay, so these are the test signals, 5 test signals let us consider. Okay, now if I apply all these 5 signals to one control system, then what will be the output for that particular control system is that with respect to time t. Okay, so let us see how these inputs can be applied and what output you will get. Okay, now first we will take here is the impulse input, or simply you can call it impulse response. Okay, so you know what do you mean by impulse response? It is represented by delta of t, and if you take in terms of in the time domain, it becomes t. If it becomes in discrete, then it becomes n. Okay, so therefore for any impulse response, okay, at time t is equal to 0, you will have a value delta of t is equal to 1. You can see in the figure here, at t is equal to 0, I have delta which is equal to 1, but at t which is not equal to 0, then it becomes 0. Okay, and how we represent in terms of Laplace domain, that is Laplace transform of delta of t or Laplace transform of r of t is equal to 1. Always, it is always. Okay, then we have a step signal or unit step signal. Okay, and how we represent this step signal? It is represented as a constant line, a constant command. Okay, such as kind of some position. Okay, you can take an example of an elevator. Like elevator is a step input. Step in the sense, for one input it will give one input. For other input again it will have all the constant terms. Okay, so therefore, if you look at this figure second figure, okay, at point 0 or at time t is equal to 0, it is equal to 1. Okay, it is equal to 1, and for all the t's greater than 0, okay, if it is greater than 0, then again it will have 1. So in general we represent it by u of t is equal to a for t greater than 0, and if u of t is equal to 0 for t less than 0. Okay, and how we represent in terms of Laplace is Laplace transform of r of t is equal to a divided by s, and a can take any value here. Okay, now we have one more input to the control system is the ramp input. Okay, so ramp is represented by a linear increase in the line, okay, towards time t or increasing time t. As you increase the value of t, then your slope will increase, your slope will be get multiplied for that particular number also. Okay, linearly increasing in the input command. So r of t is represented by at for t greater than or equal to 0. okay, but for t less than 0, r of t is equal to 0, and we represent it by Laplace transform of r of t is equal to a divided by s square. For unit it is a by s, for ramp it is a divided by s square. So we have the another two more inputs to the control system here. So one is parabola, okay, just like your exponential increase with respect to time t, okay. It is just like the rate of change of velocity of is acceleration, then you represent this acceleration in a parabolic function. So it is represented by r of t is equal to a, it can take any value again here, so a multiplied by t square divided by 2 for t greater than equal to 0 and is equal to 0 for t less than 0, okay. So here we just multiply how we find the Laplace, that is Laplace transform of r of t is equal to a divided by s cube. We have the last is the sinusoidal input. It is the input of varying and steadying the system frequency response. Here this last part of the input is very important here. We will use this sinusoidal input to this particular time control system to obtain the time response analysis, okay. So how we represent r of t is nothing but a sine omega t. So omega can also be represented as 2 pi ft, 2 pi f, so therefore it becomes a sine omega 2 pi f, a sine 2 pi f t, and it should t greater than or equal to 0, okay. Then once you understand the concept of these signals, 4 to 5 signals, you know what is transient response and you know what do you mean by the steady state response, okay. So after studying the transient response, we go for steady state response, okay. So in this, from the figure, the steady state response can be defined, okay. Some part of the output response where the output signal remains constant, you know, just by looking at this particular figure, okay. You can see after transient response your steady state response is becoming constant. So therefore once you apply all the 5 inputs to any control system or some system and whose output is getting constant or whose output remains constant, then such type of response is called as steady state response, okay. And it is represented by some parameter, okay. But if you want to obtain the steady state response, then you may find some kind of error, and the error is defined as steady state error represented by ESS. For the better operation of your control system, you need to calculate this parameter, that is steady state error represented by ESS. And how we represent or how we define the steady state error is, it is the difference, okay. So how we represent the error signal in the control system, that is R of S is equal to E of S plus or minus the feedback signal, B of S you can take or C of S you can take, okay. And how we represent here, the error signal is the difference between the input and output, okay. So error signal is nothing but it's the difference between input and output. And how we represent in terms of error, the steady state error is represented at error at time t is equal to infinity. So you can see the formula here that ESS is equal to limit t tends to infinity E of t which is equal to limit s tends to 0 in Laplace domain, so s multiplied by E of s. Then once you go for finding the steady state error, we have the another topic here, okay, which will show you how this is remaining helpful while if you go for calculating the steady state response, okay. So basically when you go for studying the steady state error, it is a static error coefficient, okay. The response that remains after the transient response has died out is called as steady state error. Died out in the sense what, after some time t your system will not respond, it will dies off, it will not give you any kind of output, okay. That comes under the steady state. And the other steady state says that the steady state response is important to find the accuracy of the output. To find the accuracy of the output is nothing but at what particular time t you have a minimum error, then that error will help us to find the other calculation part, okay. We will see one by one how that can be improved or how that can be obtained, okay. Then the difference between the steady state response and the desired response gives us the steady state error. Basically, we have three types of error here. One is Kp, it is called as positional error constant, represented by Kp. We have velocity error constant, we represent it by Kv, and we have acceleration error constant, we represent it by Ka. And all these three error constants are static error coefficient. Okay, for any error we have some kind of coefficient, and these three are the coefficients. Okay, and these three will help us to obtain the accurate output after analysis. Okay, and other than that, these static error coefficients, they have the ability to minimize the steady state error. The minimization is more important rather than completely removing the error. To remove the noise, it is not possible 100%, but to minimize the noise, it is possible. Okay, and this is how we represent the steady state error. So if you have the input like this type, that is step, ramp, and parabola, then you may have the error represented by 1 divided by Kp, 1 by Kv, and 1 by Ka. Okay, and based on the type of a system, or based on the type of the control system, whether it is a type 0, type 1, or type 2, all the values obtained for value K are different. Okay, we will see one by one how the value of type 0, 1, 2 are obtained for this particular Kp, Kv, and Ka. Now look at this figure here. Okay, in this figure we have an input R of S, a summing point. Okay, we have G of S and we have Y of S, and the error signal is represented by E of S. Okay, so when you apply some input to the control system here, this particular control system will give you some kind of error, and that error you need to obtain. Okay, and once you apply the input, and when your system will respond to some value, and once it enter into the steady state response, you need to find the steady state error. One example they have taken is unit step. Unit step, at from time t is equal to 0 till t, all the values are 1. Okay, that is just like it is a 1, then your response will be like this. Okay, you can see there is an increase in the amplitude, then fall, then go on, then it will die. Okay, die in the sense just like it's a settling time, it will settle after some time. Okay, completely dies off. So in this way we try to obtain the response. We have some kind of specifications with respect to the time, okay, or a control system, okay, which are nothing but some requirements associated with the time in terms of the closed loop system. We have seen that the control systems are categorized into the closed loop systems and the open loop systems. Okay, so what happens if I try to find the response of the signal or response of the system, if it is a closed loop system or whether it is an open loop system? Then the requirements are specified by the behavior of the control variable. We will also study the behavior of the control system, okay, or by the control error on the well-defined test signal. Try to analyze the E of S signal, then try to go for finding the control variable for the given behavior. And the last point says is most of the important test signals is a unit step, because we have 5 signals. So out of 5 signals, most of the test signal, they are not telling the actual signal, they are telling the test signal. So most of the time the test signals are basically the unit step signal, okay, of the control system, and the requirements are placed on the behavior of the control variable. Now the other thing, other than this, we have some definitions called the maximum overshoot, represented by MP. Okay, so what this maximum overshoot is nothing but it's the magnitude. I have told magnitude, or you can take it in terms of the peak. Okay, peak value or the magnitude of the overshoot after the first crossing. You can see if this is my 100% line, and if my applied input signal is responding me beyond the 100%, beyond 100% I'm telling, okay, how much it will respond, you can, then we will calculate that particular value by this arrow mark. Okay, if it is crossing my steady state value, that is 100%, then the maximum overshoot can be obtained beyond 100%. Okay, and what is the overshoot here? It is nothing but it's the peak time required to reach the maximum overshoot. How much amount of time is required to cross the 100% and reaching beyond the 100%. Okay, then what is settling time here is the settling time is the time for the controlled variable first to reach and thereafter remain within the prescribed percentage of the steady state value. Okay, for example, if I've applied some input to the control system and it is reaching to its maximum point, then after reaching to its maximum point, then my system will enter into my steady state response. Steady state response, that response also I will try to define by some steady state value. It can be common values like 2% of the applied input, 3% of the applied, 5%. Then if you go for calculation of the 2, 3, 4 and 5%, then you will find this settling, that values will be inside the settling time. Okay, then the rise time is nothing but the rise time is the time required to reach the first steady state value, that is 100%. Okay, so from 0% to 100% gives me the rise time. This is the overshoot time. Okay, and this is the settling time. So there are three definitions we can obtain from any time response analysis. We have some limitations of the time domain analysis. So the various limitations of the time domain analysis are: the control system analysis is carried either in time domain and frequency domain. Basically, we have two domains. One is time domain, another is frequency domain. But the calculations what we do in frequency domains are far better than time domain. Okay, it is easy to apply the formula, it is easy to go for the calculation, easy to simplify the system equations in frequency domain rather than time domain. The reason is the time domain requires more time, more design requirement than compared to frequency domain. Okay, then the second thing says that if you do the analysis in frequency domain, then the analysis will be very simple and it is very fast than compared to time domain. And what about the stability? The stability determination using the frequency response can be done very quickly with no efforts. The last says that in time domain analysis, the analysis becomes cumbersome. Cumbersome in the sense it becomes more difficult for the system of higher order. Higher order in the sense if my order is less, for example, first order, it becomes a bit easy. If I increase the order by 1, 2, 3, 4, beyond that order till n, then the time domain analysis becomes very difficult for the calculation. It becomes very tougher job for us to go for calculation in time domain. So that is the reason the frequency domain analysis is preferred than compared to time domain. In order to go with lesser effort, lesser analysis, we prefer time domain analysis rather than we prefer frequency domain analysis rather than time domain analysis. So with this, we conclude here that the time domain analysis are better than, frequency domain analysis are better than the time domain analysis, where we achieve the very good performance for the given system function or for the given input. Thank you.